I want to first say hello to the students here and to the students across the Atlantic. In this lecture today, I will be talking about some aspects, concepts, and nature of science. Science, as we all know, is a very important institution in our society and a very important achievement of the humankind. As you know, there are many different sciences, and there is a classification of sciences that I can give you. Sciences can first be divided into two kinds. Oops, this is not very good. We have empirical sciences and we have formal sciences. Well, in the empirical category, we'll have two other categories, but let's first talk about what empirical means. Empirical means it has to do with 5 senses or more if we have more senses. We are traditionally familiar with the 5 kinds of sense organs: vision, audition, tactile senses, and so forth. Our sense organs are our interface with the world, and we get information from the external world through our senses. And empirical refers to that process or quality. Anything that has to do with our sense organs or the information gathered through our sense organs would be empirical. Our way of getting in touch with the world by our senses is, of course, doing either observation or experiment. I will talk a little more about observation and experiment in a moment. Let's also divide empirical sciences into two, as I said. We have natural sciences and also social or human sciences. Natural sciences are sciences like physics, chemistry, biology, astronomy, anything else? Geology, for example. These sciences study in empirical ways the nature that is, let's say, outside of humans. But the social or human sciences include sciences such as sociology, psychology, anthropology, what else? History, and economics, and so on. Those empirical sciences which deal with humans and human behavior and their society and the other aspects of their life. Non-empirical sciences, another word for formal sciences would be non-empirical. These basically include logic or formal logic and mathematics. These sciences, logic, mathematics, there may be some others like computer science or maybe, I don't know, information theory, which can be classified under formal sciences. These do not take interest in the empirical world, but they have their own world, so to speak. They are not interested in making any observations or experiments, unlike the empirical sciences. And they are, let's say, interested in studying some kind of a world of abstract or idealized or perfect mathematical or geometrical objects. In the case of logic, of course, it will be the abstract world of propositions, their logical relations, arguments, for example, and so on. Okay, so from now on, when I say science, I will mean empirical science, not formal sciences. There are, of course, other disciplines than sciences. Philosophy is one of them. Engineering, medicine, arts, law, religion or theology, which is the study of religion, and sports. There may be others that I have left out. What are the differences between empirical sciences and those other disciplines? Let's take a look at, for example, the difference between empirical sciences and engineering. Engineering, of course, is a branch of study or a discipline which makes a lot of use of knowledge gathered from sciences, especially natural sciences. But the focus of engineering is to improve human life, to give them better conditions for living, giving them better conditions for travel and feeding themselves and so on. But in sciences, we don't find that focus. Sciences, especially pure sciences as opposed to applied sciences, are not quite interested in improving human lives. That doesn't mean, of course, they don't give a damn about human lives, but their focus is different, their interest is different. They are interested in studying nature to understand it, to be able to predict it, to be able to describe it, whereas engineering also adds the concern about improving human lives. Medicine is another study, another branch of study, which is in some ways like engineering, because medicine, although it makes large use of biology, biological sciences, for example, medicine is basically interested in improving human health or curing people, finding ways of dealing with all kinds of diseases that we know, including cancer and, give me some more, Headache, okay, that's a good example. And, you know, stomach ache and other medical problems that we have. So medicine is also interested in improving a certain aspect of human life, namely human health. Okay, let's take a look at the difference between sciences and arts. Arts, of course, is a very important part of our culture and society. There are also many different kinds of arts. Science is interested in finding the truth about the domain of study it is interested in. Physics is interested in, for example, finding out the truth about the physical nature, physical universe. Biology is interested in finding out the truth about organisms. Arts, as such, is not as much interested in truth as are sciences. The interest of arts is to, it's hard to describe what arts in general do, but they don't quite pursue truth about the universe. Arts, for example, literary arts produce fictions, which are, of course, not truthful. But the purpose of arts is to give some other message or to convey some emotional states to people, rather than finding out the truth. Okay, science and religion, for example, are also different. Religion and science differ in their, let's say, methodology. Religion, just like sciences, is also interested in truth, by the way. What religion tells you is supposed to be a truth about the world, or some very important aspect of the world. So religion is interested in truth, but it's not like arts in that it doesn't quite pursue, constructing fictions about the world, unlike arts. The difference between science and religion is in their methodology. Science pursues truth by allowing criticism. A scientist can advance a theory, a scientific theory, which is open to criticism by other scientists, open to criticism by other experiments or by theoretical considerations. But religion is not like that. Any religion is not quite open to criticism in its most basic creeds or beliefs. That's why a lot of people describe religion as dogmatic, as opposed to argumentative or empirical. As you all know, any religion have a core of basic beliefs which are not open to change or criticism or even debate. If you start debating those basic beliefs of any religion, then you, by definition, go out of that religion. But in science, when you criticize, for example, relativity theory, you're not out of science, unless your criticism is really, it doesn't make any sense. Okay. A little later, I will talk about certain beliefs that science or sciences have, which are also not open to debate because scientists assume them as true without quite debating about them or opening them to criticism. I will talk about those aspects of science in a moment. Okay, science versus philosophy. The difference between science and philosophy lies in their methodology. Philosophy, at least a large part of philosophy, is also interested in truth, in finding out truth about the world in general. So in that respect, it is just like sciences, but the way philosophy pursues truth is not like science. Philosophy does not conduct experiments or observations in the way scientists do. We say science has an empirical methodology. I'll be talking about this also in a moment. Whereas the methodology of philosophy, or at least a large part of philosophy, is conceptual analysis. Philosophy is interested in not doing experiments or empirical observations, but in understanding, in analyzing our concepts and the relation between our concepts and the world. Okay. Also, we talked about sports as a different discipline than science. Sports and science, well, sports can use some knowledge that is introduced by science, of course. So some sports people would like to use, the data from sciences. But the purpose of sports is not to do any experiments or to pursue truth or, it doesn't produce fictions. That's not quite the way sports work. Well, you all know the difference between sports and sciences, so I don't want to go into it. The purpose of sports is a lot different from the purpose of science, obviously. Now, functions of science. What does science do for us? Again, remember that when I say science, I have in mind empirical sciences. What science does for us is to describe the world. It also explains the world for us, explains phenomena that we come across, and it predicts phenomena. Science makes predictions about what will happen. Explanation is explanation of what has happened or what is known to have happened. Prediction is something that tells us what will happen in the future. And it's a very important function of science, prediction. Description is obvious, I guess, just describes how the phenomena, what the phenomena are, how they work, and what are their interrelations, what kind of theories can be used to describe the phenomena, and so on. Okay, let's talk about now some of the things that a scientist does. Well, observation is obviously one thing that is very common in empirical sciences. Scientists observe the world. To do that, they use various instruments. In the past, well, several centuries ago, observation relied mostly on observation by naked eye, but now we have all kinds of very sophisticated apparatuses, including, for example, this Large Hadron Collider in Switzerland. Was it in Switzerland? Or CERN, the laboratory. Okay, it's very complicated, very expensive too, by the way. Experiment is another thing, of course, scientists do all the time. Experiment is a kind of observation. It's a kind of observation, but let's say it's a kind of arranged observation. You set up the conditions for observation, sometimes very artificially, and in that case you are doing an experiment. Observation usually refers to what you kind of passively observe in the world without interfering with it, but experiment involves interference. You set up something, you arrange something, you organize the observational conditions, and then you are doing an experiment. Discovery, of course, is a very indispensable part of science and what scientists do. Scientists try to discover what is out there in the empirical or physical world. And sometimes discoveries can be very difficult, and sometimes they can happen by chance. We have examples of all sorts in the history of science. Scientists also formulate hypotheses. A well-known example would be a hypothesis that the Earth is round, which by now we all know it is true, but once it was an hypothesis. Or you can talk about the hypothesis that there is dark matter and dark energy in the universe. You can talk about the hypothesis that there are such things as Higgs particles. Those are very high-level hypotheses. A hypothesis basically is a claim about the world which we would like to test to see if it is true or false. Which brings us to hypothesis testing, which is another important function of scientists. Once you have a hypothesis, once you come up with a hypothesis in your mind, you have to see if it is true or not. So you do the appropriate experiments and observations to see if your hypothesis will be confirmed or disconfirmed. So hypothesis testing is essential. As I mentioned a moment ago, explanation and prediction are also very important parts of scientific activity. You explain a given observation and you try to predict what will our observations be in the future? Okay, let's talk about some concepts that we find in science, that scientists use, some concepts that scientists use. We have already seen hypothesis. As I said, hypothesis is a claim, is an empirical claim that is a candidate for testing. You have an hypothesis and you want to test it. Before any serious testing, it is still an hypothesis. Once an hypothesis becomes well tested or well confirmed, it can become a scientific law. So scientific laws are, in at least one sense of the expression scientific law, is a well-confirmed hypothesis. We talk about, for example, the Archimedean law, Kepler's laws, Galilean law of free fall, etc. These are so well tested that we call them laws. We also have the notion of scientific theory. Scientific theories are complicated hypotheses, or once a scientific theory gets well confirmed, it can become composed of scientific laws. An example of a scientific theory would be the Newtonian theory of mechanics. The Newtonian theory is composed of 4 claims. One is the law of inertia, the other is the familiar F equals ma, as you all know. And there is the law of action-reaction. And then the 4th one in Newtonian theory is the law of gravitation, which states that all the objects in the universe attract each other, no matter how big or how small they may be. Okay, let's talk about theorem. It sounds like theory, and a lot of people confuse theory and theorem, but they are not the same thing. We talk about Newtonian theory, but not Newtonian theorem. A theorem refers to a systematized body of knowledge, systematized in the way of axiomatization. You axiomatize a body of knowledge, for example, geometry or mechanics or optics. Once you have your axioms in place, then you can derive consequences, logical consequences of those axioms, and those logical consequences are called theorems. So in order to have a theorem, you have to have an axiomatic system. You may be familiar with the axiomatic system of Euclidean geometry. You know, it has certain axioms, and you prove theorems on the basis of those axioms. A scientific theory, on the other hand, does not have to be axiomatized. Okay, so a theorem and theory are different things. We find a lot of talk about theorems in formal sciences, by the way. They occur in empirical sciences also. There are theorems in electromagnetic theory or optics and so on. But again, a theorem is something that implicitly or explicitly refers to an axiomatic system. Okay, axiom. What is an axiom? An axiom is a proposition or a claim that is taken to be true or seems to be true, and an axiom is not tried to be proved. You don't try to prove an axiom. Unlike a theorem, you try to prove theorems by using axioms. But axioms are left unproved for certain reasons, which I don't want to go into. So an axiom is an unproved claim, which hopefully is so clearly acceptable that nobody bothers trying to prove it. But a theorem is something that needs proof. Postulate, the word postulate, maybe I should write it down. A postulate in today's usage is the same thing as axiom. Really, axiom and postulate are synonymous words in today's usage. In the past, maybe there were differences in the meanings of the two terms, but today they are taken to be the same thing. In science, we also have models, scientific models. Think of a smaller scale model of an aircraft. It's like a toy aircraft, but scientists don't intend to play with it, but they want to use it for testing some hydrodynamic or aerodynamic theory or something. They use a wind tunnel. They put the small-scale aircraft in the wind tunnel, and they study some reactions and responses that the model will give to the wind, which is very important, especially when you are trying to understand or study the feasibility of a new aircraft design. These kinds of models are iconic models. Sometimes an atom is likened to the solar system. In the solar system, we have the sun at the center, and in an atom, we have the nucleus, and the planets, revolve around the sun. And in an atom, electrons revolve around the sun. Although this is not quite correct, as we know from quantum theory, it's not that simple. But at least when you try to teach school kids what an atom is like, you can use that as a model. These models, physical models that are like the thing that is being modeled, are called iconic models. Iconic models. So the solar system would be an iconic model for an atom, and the toy aircraft would be an iconic model for a real aircraft. There are also, of course, mathematical models, which are expressed in the language of mathematics. Both iconic models and mathematical models have some similarities with the thing they're modeling, in the sense that there is a one-to-one correspondence between the elements of the model and the elements of the thing that is being modeled. Okay, now let's talk about some of the methodological principles and concepts of science. The principles I'm going to talk about apply to hypotheses or theories, regardless of what phenomena these hypotheses or theories are talking about. Well, one element of scientific methodology is to formulate a hypothesis. We know what a hypothesis is now. And then test it by empirical evidence. In empirical sciences, you don't just formulate an hypothesis. You have to test it. You have to make it believable by other people. The other element, of course, is to use logic. Logic is a formal science, yes, but logic is very useful in scientific reasoning, in the argumentation of empirical sciences also. In logic, we have two kinds of arguments or inference. Argument, inference, the same thing for our purposes here. We have deduction, we have induction. Well, I don't know if you have taken any class on deductive logic or not, but there are many rules of inference in deductive logic, like modus ponens, modus tollens, reductio ad absurdum, the chain rule, and so forth. I'm not going to discuss these here, but deductive inference has certain rules. For example, when you have a claim that says if P, then Q, and then if you have another claim that says P, you can say, on the basis of these two claims, you can infer, in other words, that Q. This is an example of the rule, deductive rule called modus ponens. There are many other rules. Induction, on the other hand, is different from deduction. In deduction, we are looking for our argument to be such that if you assume its premises to be true, you would have to accept that the conclusion is also true. So this would be called a valid deduction. If you assume the premises, all of the premises to be true, then you can't avoid accepting the conclusion. That would be a valid deduction. In an inductive argument, on the other hand, there's no such requirement. You have your claims. Let me just show them like this. I claim this, I claim this, I claim this, and then I conclude, therefore, something. Maybe I should have been more sophisticated and used variable letters instead. Like, suppose I claim A, and then B, and then C, and I infer, therefore, D. In an inductive argument, you don't look for the structure of the argument to be such that if you assume all the premises to be true, you have to accept also the conclusion to be true. That's in deduction. In induction, if you assume or accept all the premises to be true, the conclusion becomes acceptable to some degree, preferably to a high degree. So the conclusion of an inductive argument follows from these claims, which we call in logic premises. From premises, the conclusion follows with some high probability if the inductive argument is good. And that's all you need. That's all you look for in an inductive argument. Your premises, your claims here make your conclusion here plausible to believe. There are different kinds of induction also. For example, induction by enumeration, analogy, inference to the best explanation, and so on. These are different kinds of inductive arguments. And one very important thing in science or in any field of discourse, I would say, is to avoid contradictions. We try to avoid contradictions, not just in sciences, but also in daily life. We don't want to contradict ourselves. Contradictions are something that we don't want. So scientists should be very careful to avoid contradicting themselves, having their theory contradicting with some other more accepted theory, and so on. So avoiding contradictions is a very important logical concern in science. Here's another aspect of scientific methodology that may escape notice. In sciences, we use, I still have empirical sciences in mind, we use idealizations and approximations to simplify an hypothesis or a problem. Using approximations and idealizations is inescapable, unavoidable in science. Because when you're dealing with a phenomenon, your theory cannot account for all of the factors that surround the phenomenon. Okay? So what you do is you make simplifications by idealizing and approximating. You assume, for example, the surface that the thing is moving on is frictionless. Or you assume that there's vacuum conditions. Because if you also take into account the real conditions, the problem will be too complicated to treat with mathematics. Mathematically, it will be unmanageable. That's why we use idealizations and approximations. There's another principle used in science without many scientists knowing the name for it. It's called Occam's razor. Occam was a medieval philosopher who came up with this principle. This principle says, if you have two theories which explain and predict exactly the same phenomena, choose the simpler one. Don't bother with the more complicated one. So look for simplicity. That's a principle that scientists knowingly or unconsciously use. There are other desiderata in a scientific hypothesis than truth. We have so far talked about science looking for truth. But in a scientific theory, you don't look just for truth. You also look for elegance and simplicity, which is really a consequence of the principle of Occam's razor. So elegant theory is more acceptable than others. A theory that sets forth symmetries, for example, or elegant in some other ways, would be more preferable by scientists. Is that because of their aesthetic feelings or not? I don't know, but elegance is one important consideration. Not as important as like logic, for example, use of logic in science, but it is still a factor for preference between two theories. More elegant the theory is, more preferable it is. Okay. One thing that we observe in science is the progress of science. Scientific knowledge seems to be increasing. We know a lot more than what ancient people used to know, or what ancient people knew. But scientific progress, or the advance of scientific knowledge, is not totally smooth. There are revolutions, scientific revolutions, in the history of science. The Copernican revolution, which takes its name from the astronomer and mathematician Nicolaus Copernicus. And then we have Newtonian revolution, which is due to Isaac Newton. And we have Darwinian revolution in biology. And we have Einsteinian revolution and quantum revolution and many other revolutions in science. So scientific knowledge don't seem to be increasing just in a smooth way. It is increasing in jumps sometimes. Sometimes there's a big jump suddenly and then it continues. There are also some very fundamental assumptions of science. Philosophers call them metaphysical assumptions of science. For example, all scientists assume that there is an objectively existing material world. Well, quantum people have some doubts about that, but forget the quantum scientists. The rest of the scientists assume that there is an objectively existing material world. It exists outside of us and does not depend for its existence on us. So there is an existing external world, a world that is external to us. You don't find scientists discussing whether this is true or not. Although, as I said, quantum scientists, quantum physicists, or some of them, had some doubts about whether the world, at some level, is totally independent of us or not. Another assumption made by scientists is that the world is intelligible by us, or intelligible for the most part by us. I guess even quantum physicists assume that. The intelligibility of the world. And we also, well, scientists also assume that mathematics and logic are applicable to the world. If they did not assume that the world is intelligible by us or mathematics and logic are applicable to the world, then I guess there would hardly be any science or any scientific progress. Now, these two assumptions that I mentioned are almost dogmatic to scientists. I mentioned earlier that religion tends to be a dogmatic body of beliefs, but these particular assumptions also are assumptions that are not open to discussion by scientists. Not because scientists hate someone to discuss them, but because they can't discuss them. They have nothing interesting to say about whether the assumption, for example, that there is an objectively existing material world is true or not. Or whether they have hardly anything interesting to say about whether or why the world is intelligible by us. These two assumptions, and there may be some other metaphysical assumptions of science, are debated, thought about by philosophers instead. These are philosophers' job to talk about and discuss. Because the assumption, for example, that there's an objectively existing material or physical world is not something that you can confirm or disconfirm by empirical evidence. What observation do you have to make in order to falsify or verify the claim that there's an objectively existing physical world? There doesn't seem to be any. It's a conceptual problem, and that's why it is left to philosophers to talk about. Okay, let me talk about some more terminology and notions that we encounter in science. Empirical is very important, and we explained what it is. There's also the notion of the distinction between a priori and a posteriori. You may hear some scientists or some people talk about something being a priori or a posteriori. A priori refers to a kind of knowledge that we claim to have. A priori knowledge is a kind of knowledge that is not based on any empirical observation or experiment. Are there such things? Are there any examples of a priori knowledge? Well, some philosophers have claimed that, yes, there are. A priori knowledge, or a priori, sometimes pronounced, a priori knowledge is something like, for example, the claim that everything is caused. There are no uncaused phenomena. That would be, according to some philosophers, like Kant, for example, Immanuel Kant. That would be an example of an a priori knowledge. Or some people talk about the a priori character of mathematics and logic. To find out whether our logical rules or mathematical deductions are correct or not, we don't make experiments. We just think. It's based on thinking and not any empirical observation or experiments. So a priori knowledge is knowledge that is not based on any observation. A posteriori knowledge, on the other hand, is just the opposite. A posteriori knowledge is a piece of knowledge that is based on observation and experiment. Empirical sciences deal with a posteriori knowledge because they're making observations and experiments. The knowledge of the universe we can gather through our senses will have to be a posteriori. Do they use a priori knowledge also? Yes, to the extent that scientists use logic and mathematics. We said logic is, and mathematics is very helpful disciplines for empirical sciences. What is logic, though? Logic is a discipline that studies our reasoning, what we call in logic our arguments. Logic is the study of good and bad arguments. What kind of arguments, what kind of inferences are good or acceptable or valid, and what kind of arguments are bad or unacceptable or invalid. So logic is the study of our reasoning. It doesn't quite study our brain. It doesn't study how brain works or how we do inferences in our brain, but it does something formal without making any observations about the brain or anything else. And what forms of reasoning would violate good forms? Proposition, I guess I already at one point talked about proposition. A proposition is a claim, is any claim which can be true or false. When I say, for example, the earth revolves around the sun, I'm making a proposition. Or when I say, today is Thursday, I'm making a proposition. When I say, God exists, I'm making a proposition. Proposition can mean other things, of course, in other contexts, but in the context of logic, proposition is a claim that can be true or false. You may have also seen this term, tautology. A tautology is a proposition that cannot be false. An example of tautology would be something like either P or not P. Today is either Wednesday or not Wednesday. Is there any chance of that proposition being false? No. Because of the way it is constructed, a tautology is a necessarily a true statement, as we say. Some people call these kinds of mathematical statements also tautologies. A tautology, when you talk about a tautology, strictly speaking, you have in mind some formal system, some logical system. Either P or not P is a tautology in the classical logic that we know about. In some other logical system, this may not be true. In fuzzy logic, this kind of a statement is not a tautology. It can be false. Okay. When somebody says, you are giving me a tautology, what this person probably intends to say is that what you are saying does not give me any information. Because a tautology does not convey any information. Because it is necessarily true, there's no way of denying it, and there's no way of, finding out whether it is false by making any observations. It is trivially true, so to speak. Premise, another term that logicians use and scientists also use. Premise is a claim in an argument, such as this, which are intended as evidence for the conclusion. In this argument, we have these two premises, and this is the conclusion, Q is the conclusion. And these two are intended to give the ground or evidence for the conclusion. If your argument is a valid argument, your premises make your conclusion necessary or 100% true. If your premises are assumed to be true, your conclusion has to be true, 100% true. Okay, two concepts are also frequently used in science. Those are consistency and inconsistency. People talk about the inconsistency of a theory or something that somebody says, or the consistency of something with something else. Consistency is really a logical concept. When you say something is consistent, that means it doesn't involve any contradictions. There's no contradiction in it. And when you say something is inconsistent, when I say something, of course, I mean something that is said is inconsistent, that means it involves a contradiction. We would like to be consistent, of course, all the time, rather than inconsistent, and what you are saying is inconsistent would be an accusation of some seriousness. What is then a contradiction? If consistency means lack of contradiction and inconsistency means presence of contradiction, what's a contradiction? Contradiction is a logical term which refers to statements like P and not P. When you say both P and at the same time not P, you are contradicting yourself. This is a contradictory statement. Compare, by the way, this with this. This is a tautology, an example of a tautology. This is a contradiction. There are other examples of contradictory statements also, but let's consider this one. This statement is necessarily false. There's no way that this can be true. No matter what P is, what proposition P refers to, P and not P would be always false. And this will be always true, no matter what P is. Contradictory statements are, under all circumstances, false, and therefore, since we don't like falsehood, we would like to avoid contradictions. A related notion that you sometimes find in empirical sciences as well as in some other disciplines is paradox, the notion of paradox. What is a paradox? What is paradoxical? A paradox is akin to the concept of contradiction, but it's not quite the same thing as a contradiction. A paradox is a situation where you have an argument or inference to some claim, let's say A, therefore A, at first sight, the inference looks okay. It seems like the steps of reasoning that arrive at the conclusion A are all fine, logically speaking, by logical standards. But A is something that you don't want to accept. It can be a contradiction, or it's something that is totally implausible. Let's give an example, actually, a quick example of a paradox. The most famous paradox, perhaps, called liar paradox. Some Americans call it the lawyer paradox, but there's just a joke here. When you say this statement is false, we expect such a proposition, such a statement, to be either true or false. It can be true, it can be false. Okay, is it true? It's hard to decide. Is it false? Hard to decide. So let's consider two possibilities by opening up two branches that indicate the two possibilities here. This statement is false may be a true statement as a whole. It may be a false statement as a whole. Okay. Now, can this statement is false be a true statement? If it is true, then what it is saying is true. But what it is saying is that it is false. So if it is true, then it follows that it must be false. So you cannot assume it to be true because you end up with the conclusion that it must be false. On the other hand, let's suppose that this statement is false is a false statement. Can it be a false statement? There's no hope here, it can't be true, so could it be false? Look, if it is false, if it is in reality a false statement, then look at what it says. This statement is false. Then it is telling us the truth. It is false. And so therefore, this statement is true. So we end up concluding that it must be a true statement. So this statement is false, can neither be true nor false. But then what else could it be? Well, this is one of the oldest paradoxes that we know of. Sometimes it's also called the Epimenides paradox. This is a version of Epimenides paradox. Although it is very old, maybe 2,000 years old, we still don't have a solution that would be acceptable to everybody. It's still being disputed. How can we get rid of this paradox? How can we resolve it or solve it? And it's still an alive paradox. There are many examples in the history of philosophy and logic of paradoxes, such as the surprise examination paradox. You may have heard about it, or Sorites paradox. There are even paradoxes in sciences. In physics, for example, there's the so-called Ehrenfest paradox, which of course I'm not going to discuss here. I just want to note that there are many paradoxes that we know of, and those paradoxes are still awaiting solution, such as the liar paradox. Okay, so a paradox is a situation like this, where apparently correct steps of reasoning, or an apparently correct sequence of reasoning, leads us to an unacceptable conclusion. What is the unacceptable conclusion here? The conclusion is that this statement is false, cannot be false, it cannot be true either. So what else could it be? Okay, so that's an example of a paradox. Let's talk about some other terminology and notions that every intellectual must really know about. Not just scientists, but every intellectual. For example, what is objectivity? What is subjectivity? You hear these words a lot of times. We want to say that science is objective rather than subjective. So what is it to be objective? Let's talk about subjectivity first. Subjectivity refers to the condition when somebody is under the influence of his or her prejudices, antiquated beliefs, perhaps very old beliefs, his or her own preferences. If these elements of someone's personality are reflected in that person's beliefs, then that person is being subjective. You can accuse someone of being subjective. You are being very subjective, you say, which means you are letting your prejudices and preferences interfere with your beliefs or claims. A scientist is supposed to be not someone like that. The scientist's subjective opinions, preferences, emotional states, personal preferences should not interfere with the scientist's work or theory. So objectivity is the opposite of subjectivity. When you're dealing with the world scientifically, you must keep all your prejudices and other beliefs, personal and subjective beliefs aside, and look at the phenomena as it is. That is objectivity, and it's a big requirement of science. It's a matter of philosophical debate whether science can be purely objective, whether there are subjective elements also involved in scientific activity, which we are not going into here. Another concept is the concept of rationality. Rationality. We all want to be rational. But then what is rationality? It is hard to define exactly, precisely what the rationality or rational is, but here is one old suggestion for a definition of rationality. If someone makes his or her beliefs proportional to their evidence, then that person is being rational. In other words, if you have little evidence for some big claim, then you are not rational. You lack rationality. You are being less than rational. On the other hand, if you have a huge body of evidence which point to the truth of a certain claim, but you tend to not accept that claim, despite the huge body of evidence, then you are also being not rational. You are being irrational. So rationality is a matter of evidence. Speak to the extent that your evidence allows you. Anything more or less than what your evidence warrants, then you are being less than rational. Logic, by the way, which is a study of reasoning, we said, is also the study of rational forms of reasoning. The example we gave here, a very simple example. If you accept these two premises, you have to accept the conclusion Q is a rational rule. Someone who accepts these two premises but denies this is not being rational. So a valid argument in deductive logic is a model of rationality. But rationality is not found only in deductive logic. It can also be found in inductive logic. If your evidence is strong for some claim, but you refrain from believing the conclusion, then you are not being rational. Rationality also is a term that we use in daily life. Someone may say to somebody, you are not being rational. Someone, suppose, spends his or her money without thinking what is in store for that person. Then we say this person is not being rational, because then he or she will be in trouble in the future, because he will be left with no money. So in daily life also there are forms of irrational behavior or irrational belief. Of course, in science, rationality is very important. All scientists want to be rational and avoid irrationality. Okay, one more important concept is the concept of concept. What is a concept? We use the term all the time. You don't have a concept of this, I have a concept of that, and so on. But what is a concept? What a concept is something hard to define, and it's a difficult philosophical problem. The exact status of concepts itself is a philosophical problem, which I don't want to go into. So instead of talking about what a concept is, instead of trying to define it, let me talk about what it is for someone to have a concept of something. When I say I have a concept of glass, that means I can use sentences in which the word glass occurs correctly. If I say, for example, there's a glass on my table, then I'm making a correct sentence, and I believe that it's correct. If I say that there's no glass on the floor, then again, I'm saying something correct. If I say there are glasses in space, outer space, that will be a false statement, and I know that it's false. So then I must have a concept of glass, because I know how to use it correctly, how to use the term that refers to the concept correctly. Someone who has the concept of a cat, for example, knows how to distinguish between cats and other things. Someone who has the concept of cat does not confuse cats with crocodiles or glasses or planets. So that person would be said to have the concept of cat. Okay, one more notion that you find in science. the notion of theory reduction. Sometimes we talk about a theory being reduced to another theory. What does that mean? What does it mean, for example, to say that biology can be reduced to chemistry, or chemistry can be reduced to physics? I don't know if these claims are true or not, but let me tell you what they mean. What does it mean to say that chemistry is reducible to physics? Well, in order to reduce one theory to another, well, the board got too crowded, so let me raise a bit. Theory A to theory B. In order to say that you have reduced theory A to theory B, you have to do two things. You have to first define all the terms of theory A in terms of the terms, well, we have too many terms. To define all the notions, let me say, or concepts, notions of theory A in terms of the notions of theory B. Secondly, be able to derive Derive is something like deduce. A derivation looks like a deduction. You have to be able to derive all the claims or propositions of theory A from the claims or propositions of theory B. If you can accomplish these two tasks, well, this is, of course, a very rough formulation. There are a lot of details that you have to be careful about, but let's roughly speak here. If you accomplish these two tasks, then you can say, I have reduced theory A to theory B. To reduce chemistry, for example, to physics, you have to be able to define all the terms that chemistry uses, all the specific terms that chemistry uses, in terms of the terms that physics uses. For example, I guess chemical reaction is one term that chemistry uses, so you have to be able to define it in terms of physical notions. Secondly, you have to be able to derive the claims of chemistry from the claims of physics. For example, one, let's say, simple law of chemistry is that salt, the table salt, the ordinary table salt that we all know of, is soluble in water. Okay. Physics will have to be able to explain it or drive this claim from its own terminology and laws. Physics can do that, presumably, by talking about the interaction and the forces, molecular forces between salt molecules and water molecules, and then explain this phenomenon. I don't know how that can be done exactly because I'm not a physicist, but I'm sure it is done. So similarly, for all other claims of chemistry should be derivable from the claims of physics, in which case you have done both of the two things, and then You can talk about reduction of chemistry to physics, for example. Similarly with reduction of astronomy to physics or biology to chemistry and so forth. Theory reduction is something that scientists are interested in because deriving many different theories from a single theory would make those sciences more systematic and easier to handle from a logical point of view. Finally, let me talk about another concept that is often found in science, especially physics, the concepts of determinism and indeterminism. Determinism is the claim that everything that occurs has determining causes. In other words, every event has previous events which caused it. So there is no uncaused event, according to determinism. Indeterminism is the opposite of that, the claim that in the universe there can be uncaused events, events which don't have any prior causes. The question whether our physical universe is a deterministic universe or indeterministic is a matter of dispute, especially after the advance of quantum mechanics. According to one interpretation of quantum mechanics called the Copenhagen interpretation, our universe at the microcosmic level, in other words, at the level of microparticles, atoms, electrons, photons, positrons, etc., at that level it is probabilistic or indeterministic. Everything that occurs at that level obeys probabilistic laws rather than deterministic laws. So indeterminism gives us probability rather than determinism. So today we have talked about some of the basic concepts, basic terminology, and the nature of science. There is a lot more to be said, of course, but this was just an introduction to these matters. Let me ask students here, do you have any questions? Yes.
Can you give a few examples of scientific questions and philosophical questions?
Okay. We said earlier that questions that philosophy deals with are different in kind from questions that empirical sciences deal with. We said in terms of their methodologies, science follows what we can roughly describe as empirical methodology, which involves formulating hypotheses and testing them and so on. Philosophy does not make any empirical observations as such. Philosophy does not make any observations in the way that empirical scientists do. We said philosophy is a conceptual discipline. Its methodology is, although philosophy is so complicated that it's hard to describe its methodology in a few terms. But philosophy is more interested in understanding our concepts and how those concepts relate to the world. I guess that should be enough as far as a description of the methodology of philosophy. Let me give you some examples of empirical questions first, and then I will give you some examples of philosophical questions. For example, when I say how many students are there in this room, this would be an empirical question. It won't be even a serious scientific question, of course. By the method of counting how many students there are in this room, we can answer that question. Counting refers to a kind of observation. I have to observe and then count, okay? So it's an empirical question. A more scientific empirical question would be like, does wood, for example, conduct electricity? In order to answer that question, you have to set up some experimental or measurement conditions and find out if a piece of wood conducts electricity or not. It's an empirical procedure entirely. Or the question, for example, is the earth round or flat? That's an empirical question. You have to do the appropriate observations and perhaps experiments to answer that question. Another empirical question, which will be also a very scientific one, would be, what is the age of the universe? Well, scientists today talk about the age of the universe being 13.7 billion years. They came up with this figure. That answer relied on a lot of empirical observations, experiments, a complex of theorizing. In other words, the answer is obtained through a complicated structure of empirical procedures, because it's a difficult question. To give you some examples of philosophical questions, consider the question, what is time? Well, when you ask, what time is it? That's a very simple empirical question. You just look at your watch and give the answer. Looking at the watch, of course, would be a very simple empirical procedure. But when you ask, what is time? I don't think you can answer that question by looking at any watches or clocks or anything that measures time. What is time is a conceptual question. You have to understand the concept of time and how it relates to the world. You have to do a lot of conceptual analysis, in other words. It's not something that you can answer by making a certain set of observations. Again, what is truth, for example? We talk about truth, and the question of what is truth is not answerable by any empirical activity. You can't have any laboratory which you can go in and look for an answer to the question, what is truth? Or you can't have any observation instrument which would give you the answer, what is truth? It's a conceptual question again, it's a philosophical question. For example, mathematicians, to give you an example from mathematics, mathematicians talk a lot about numbers, right? At least arithmeticians deal with numbers a lot and their relations. But the question whether numbers exist, or the question whether numbers are fictitious entities that are invented for certain reasons, is a philosophical question. Do numbers exist? That's not a question that mathematicians deal with. Philosophers of mathematics would find that question interesting and try to answer it. Again, does God exist? That's a question that is philosophical. I don't know of any specific science that tries to answer that question, first of all. The question whether God exists or not is not something that you can answer by any laboratory experiment or by observing the skies or whatever. That's not the way to try to answer that question. Instead, you have to understand the concept of God, and you have to look at the world and many other things and try to answer that question. Religions, of course, don't ask that question. They claim that God exists. Philosophers, being different from theologians, they find arguments for the existence of God rather than accepting it at the beginning without any proof or ground. Okay. Well, there are, of course, many questions in philosophy that are, again, not empirical in character. For example, why should I be moral? We want everybody to be following ethical rules of morality. We want to be ethical people, right? The question is why? Why should I be moral? What is the basis of morality? Again, that question is not an empirical question because there's no way you can answer that question by any empirical method of observation or experiment or empirical procedure. What is the meaning of life? A very popular, or let me say famous philosophical question. What's the meaning of life? Again, how can you find the meaning of life, if there is one, by any observation or experiments? That's why there's no laboratories of philosophy in philosophy departments. Although there are physics laboratories, chemistry laboratories, there's no such thing as philosophy laboratory or philosophy observatory. Okay? That satisfies you? Okay. Go ahead.
There's a field called philosophy of science.
Mm-hmm.
What exactly does it do?
The field of philosophy of science is a branch of philosophy. Actually, it's a specialization, we say, in philosophy. It studies science, as the name philosophy of science implies. What it does is to try to understand various aspects of scientific activity. For example, scientists formulate theories. The philosopher of science asks the question, for example, what is the structure of a theory? What is a theory? What's a scientific theory? We mentioned many concepts and notions of science, such as observation, experiment, discovery, hypothesis formulation, theory, hypothesis testing, explanation, prediction, and so on. The philosopher of science is interested in understanding these concepts in a philosophical way. In other words, philosopher of science tries to understand things like, what is a discovery? Is there a logic of discovery? What the philosopher of science tries to do is not to discover things, but to understand the logical thinking behind scientific discovery. We talked about confirmation and disconfirmation in science. Of course, it's essential to try to disconfirm or confirm your hypothesis before you can accept or reject it. One thing the philosopher of science asks is, what is the logic of hypothesis confirmation? How does the scientist reason in general when the scientist attempts to confirm or disconfirm, in other words, test an hypothesis? The logic of confirmation. These are not the kinds of questions that scientists themselves ask, but they are asked by philosophers of science because they are conceptual questions. When you ask, for example, what is the structure of a theory, scientific theory, what's the procedure or logic of hypothesis confirmation, or the question whether there is a method of discovering something, these are not themselves empirical questions. Those are basically conceptual questions, so they are in the domain of philosophy, and in particular, philosophy of science. I hope the function of philosophy of science as opposed to science itself is now clear. Okay. All right, who's next? You want to go ahead? Okay.
Can you give some examples for a priori and a posteriori knowledge?
Okay. We described earlier a posteriori and a priori or a priori as categories of knowledge, kinds of knowledge. A priori knowledge is the kind of knowledge that we obtain without doing any observations or experiments in the world. They are, in a way, innate knowledge. We are born with such knowledge. We don't have to do any observations or experiments. For example, when I say P or not P, I know that it is true, right? I know that it's a true statement. It can't be false. It's necessarily true. How do I know that? Without resorting to any experiment or observation. By just looking at the components of this sentence, I can know that it is true. Okay? So this would be a piece of a priori knowledge. Some people, although not all, think that our knowledge of mathematics and knowledge of logic are all a priori. They don't rest on any observation of the world, but instead rest on studying numbers, their relations, and so forth, which are not things that you do in the empirical world. A posteriori knowledge, on the other hand, is the opposite of that. In other words, to have a posteriori knowledge, you refer to the empirical world. For example, the claim that the Earth is round would be an example of an a posteriori knowledge, because in order to find out whether the Earth was flat or round, we had to do the appropriate observations, right? The best way nowadays is to go to the outer space and take a look at the Earth, and then you will observe that the Earth is round. So that knowledge that the Earth is round is a piece of a posteriori knowledge. Again, for example, the knowledge that water is composed of hydrogen and oxygen molecules is a posteriori piece of knowledge, because we had to do a very complicated series of observations and experiments to come up with that kind of knowledge. It's not something that we are born with. I mean, we are not born with the knowledge that water is H2O. If we were born with that, maybe some of the chemistry classes would be easier, but that's not the case. That electrons repel each other, or that there are so many galaxies in the universe, or that organisms are composed of cells, those are all pieces of a posteriori knowledge. Okay, another question? Yes.
Yeah. My question is about logic. We talked about induction and deduction, but can you clarify the distinction between them one more time for me?
Okay, sure. Deductive logic and inductive logic. Well, deductive logic studies deductive arguments, and inductive logic studies inductive arguments. But then what's a deductive argument and what's an inductive argument? A deductive argument is the kind of argument which is such that if it is valid, then if you accept its premises, then you would have to accept its conclusion. If that's the case, it's a deductive and valid argument. Some deductive arguments are invalid, of course, which means even if you accept the premises of the argument, you don't have to accept the truth of its conclusion. As an example of a deductive, an actual deductively valid argument, let me give you the stock example of valid deductive argument that you can find in almost every logic textbook, which was originally given by the ancient philosopher Aristotle, who was the first person who gave a systematic formulation to our ideas of logic. The example is, all men are mortal. Of course, actually, Aristotle means humans, not men. And the second premise says Socrates is a man. Therefore, Socrates is mortal. Now, this argument is a valid argument. In other words, it's a good piece of reasoning in the following sense. If you accept its premises to be true, if you assume them to be true, then you would have to accept the conclusion to be true also. In a valid deductive argument, the premises actually don't have to be true, but what you need to do is to ask yourselves, if I assume the premises to be true, whether they're actually true or not, would I also have to accept the conclusion to be true? If the answer is yes, it's a valid deductive argument. Now, inductive arguments are never valid. They are always invalid, which means even if you accept the premises of the inductive argument, you don't have to accept its conclusion to be 100% true. But if there's a good inductive argument, then if its premises are true, then its conclusion would be highly likely to be true. Here's another stock example given in almost every textbook for an inductive argument. Suppose you make several observations of the color of swans. And let's say you observed 10 swans and you found out that they are all white. So you set up an argument like this. Swan number 1 is white. Swan number 2 is white. Swan number 3 is white. And so on. Swan number 10 is white. Suppose on the basis of those 10 observations, you want to conclude that all swans are white. Now, this argument cannot be valid. In other words, even if you accept its premises to be true, you don't have to accept its conclusion to be true. As a matter of fact, all the premises, let's say for somebody who observed just 10 white swans, all the premises are true. But the conclusion does not have to be true, because you can find the 11th swan to be maybe black, maybe yellow. So there's no necessity here of accepting the conclusion to be true once you accept the premises to be true. This is an example of an inductive argument which is invalid, but it is such that if its premises are all true, there's some likelihood of its conclusion to be true also. It's not totally useless, because the truth of the premises make the truth of the conclusion plausible to believe or likely to be true. That's the function of an inductive argument. Inductive arguments cannot establish a conclusion conclusively, 100% true, but they give some plausibility to the conclusion. And indeed, in empirical sciences, that's what we do a lot of times. Empirical world is something about which we cannot have certain knowledge. Our observations, our theories may all be false, right? As we have seen in the history of science, the theories which seemed to be true turned out to be false later on. So, in the empirical world, our knowledge is not infallible, it's fallible knowledge. That's why inductive arguments, being fallible, are nevertheless indispensable parts of empirical sciences. You can have deductive arguments also in empirical sciences when the empirical scientist uses mathematics, for example, some mathematical argument to establish some conclusion. The mathematician might say, a physicist might say, the mass of Jupiter is twice that of, I don't know, Saturn, let's say. I don't know if that's true or not. And then suppose, as another premise, the scientist says the mass of Saturn is 10 kilograms, which is obviously false, of course. Then the mass of Jupiter is 20 kilograms. This is a deductive argument, a kind of argument that a physicist or astronomer can use, although it's so simple that I don't think any serious astronomer or physicist would bother setting up such an argument. But still, in mathematical calculations, empirical scientists make. They are using mathematics, and mathematics is a deductive discipline. And the arguments of mathematics better be deductively valid, and therefore scientists who use mathematics are setting up deductive arguments all the time. A mathematical proof, whether done by a mathematician or a physicist or any other empirical scientist, is a valid argument if it is a correct mathematical proof. Okay? That's all for today.